I think it would have been better if I just didn't show up to class and said that I went as Neutrino for Halloween.
You should have dressed up and gone as Climate.
I was going to, but I didn't have anything that would fit. Feynman doesn't have a beard.
I was just saying I have a beard.
Congratulations.
Not with me. He said,
Why don't you
he is the original energy one-third of the center mass energy, which was not 200 watt meters. Right? Critical energy is for the the number of radiation length. Okay, yeah, that part is the number of radiation length is not dependent.
The wave function, everything in functions is a function. Okay. So like early meeting and wave function.
It's a fraction.
Yeah, that's why. So like all my code is like yeah. I didn't find it. I can find it.
I hear it goes again.
Where's your hat? I gave it back to you and you're not wearing it?
No, I am not. Leave me alone.
Makes me feel crazy.
Don't make dumb comments.
I'm practicing for when I'm a dad. Gotta make bad dad jokes.
That's not gonna happen, and you know very well.
I made an upgrade to the visualizer. Primary upgrade. Okay, the primary upgrade is things now come in color. It'll stay there. Not everything's gray. Now the scintillator is orange.
Wow.
The other thing is that spheres now work right, but the reason, if anyone tried, was it Micah that tried spheres, or was it the other class? Did you try spheres, or was it tried spheres? Anyway,
I did.
That was you, and they weren't working. That was you. Okay, yeah. Sorry. So the reason spheres don't work right is because the sphere goes all the way to a theta of 0, which corresponds to an eta of infinity. And then you tell it to split it up into rapidity, and it's like I don't know how to split up 0 to infinity, right? That doesn't work. So it gets all confused and nothing happens. So the solution is you need to tell the thing, don't go all the way to 0, right? The sphere cannot be a complete sphere. You can't go all the way to 0, or else it won't know how to split up. You can't do that anyway. There's a B pipe in the way at least, right? So what I do is this, and I put this in the document, in the document online to update it. If you're using a sphere, you know the length column, the first one, I didn't do anything with it. Now I do something with it. The length column is going to be the minimum radius of the sphere. That's say at the end, there has to be a hole in it, right? Or what's the size of that hole? So at the minimum, that should be the size of your B pipe, the radius of your B pipe. Okay? And you could make it bigger if you want. Okay, so that comes in that part, and then it seems to work fine. It looks a little funny sometimes, but as far as I can tell, the coverage should be okay. Okay, so that's that. And also and now it also, remember you don't need to put detectors on, now if you try and put a detector on a piece of iron or something that's not scintillating, it won't give you any, it won't charge you for it. Because that'd be silly. You don't need to technically come to Surveyor, right? Okay, so anyway, that's done. Okay, next. Test. So.
Wait, what? We have tests?
Yeah, you have a test today, right? No. Eden, we're doing this tomorrow, right?
Yeah.
So can I ask you to step up for a bit?
Yes.
Take her stuff with you. We'll keep you for a few minutes on it.
Okay.
They were supposed to be good. I don't need to see my test.
No, that's okay.
You have something to do? And you can take something with you if you want. I don't want to waste your time. Okay. Test one okay. Some people did better than other people. This happens.
I don't want to look. You did better than me. Shut up.
I wrote what you guys
I actually don't remember what the average is, but I can look it up.
You did better than me. It's a guarantee test. But I didn't even pass this one. I guarantee you I didn't pass this one.
check right now.
You can't. You didn't input it until you see it.
81.5. Standard deviation of 10.7 for the usual. A little high. A little high, right? Well, we've got some quizzes that high before. So, anyway. So, there are people, however, who did poorly on the test. If you are one of those, remember that there is a redemption quiz on it, as always. The redemption quiz is not till December. But like the point is, you don't be discouraged, but you need to learn how to do these, right? So say you need to realize, what did I do wrong? How can I fix it, right? Because you will have the chance to fix it. You just need to realize what you did wrong. Make sure, of course, not to write on these, to write on your own sheet of paper, right? All right, let me get these back. Russell, Maddie, Nicholas, Nisha, Kristen, Alvin.
What?
Sorry. Sabian, Harry.
As x becomes greater, y becomes smaller. Does this make sense?
John. What are you? What's that in your hair? Wait, no, don't look at it. That's not that.
No.
Oh,
It should be if x
with
gets
bated breath. Are you?
greater, y becomes closer to 1.
Are you? Excellent.
Let's look at this one. Because you have two different options. I don't like this. I don't like this at all.
Micah.
Yeah. I don't know.
Eric.
I don't think that counts as passing.
G.
It's yeah, better like that.
Ellis.
Holy.
Nolan.
Why did you leave this one blank?
I didn't. Well, I did by accident. I wrote this and then erased it by accident. So
I couldn't figure out how to do this one.
you got all of them. Like I only got one in.
MC, or do you take it?
Do we have to return these?
Probably.
Okay, I can read these just fine. I don't understand why I can't have
Why is this wrong?
Alright.
Why is this way wrong?
We can go over it. Okay. Number one had lower scores than it really should have. Like, I honestly kind of don't know. I guess maybe just the pressure of the moment or something. I think more of you know how to do this. Like, it's not like, I think maybe the letter P confused you. Because P is a positively charged baryon, it's a proton, right? And so this violates conservation of charge because this is a charge of 0, that is a charge of 1. And it violates conservation of baryon number because there's no baryons here, but there is a baryon here.
Get it right. That's why.
So it violates charge and baryon number. You do have to put both. I've been telling you that,
I didn't
for the
get
next
those
one,
baryon
okay.
So it clearly does.
So delta minus and PDE, delta bar plus.
Because there's definitely baryons in here.
And it went to some silly combination of things. Plus C is C B bar, right? C minus C bar B.
I hope you realize I'm not
Eta.
It's definitely gamma, that's a variant.
Eta here, and the eta can be anything, do you notice that? Or not anything, it can be three different things. So you get your choice, it works for any of them. Honestly, what's easiest though?
It's a squawk.
Easiest is dB bar. Oh, is it eta C? Oh, it's eta C. Sorry, that's the other class of the eta. Never mind. Forget to say anything. So, eta C is dB bar. Okay, so this one is a straightforward diagram. And then the only way to do it is read annihilations, read pair productions.
Hurry up.
I did
Alright.
everything bar, U bar, T bar.
So that's the only way to do it because none of these are repeated over here, so they all have to annihilate in pairs.
Where did we get the
All right.
U bars from?
Number 3, can we get a picture of that?
Wait, what did you do differently than I did?
It's not ready.
What did you do differently than I did?
All right.
A lot of things.
U plus goes to pi plus mu naught. Oh yeah, so the number
I
3
did
violates left top number
annihilation
because there's a
into
U plus on one side is an antiparticle,
So-
but then a neutrino on the other side is a regular lepton. So because of that, the lepton number is not the same on the two sides. Also violates conservation of energy. The mass of a pion is greater than the mass of a muon. So it violates conservation of energy as well. So two things that that violates. Okay. Number 4 has some scraps for a moment. A silly combination of particles, sigma plus plus C. The people who work with these, all these hadrons are referred to as flavor physicists. I am not a flavor physicist, so I like don't recognize any of these particles offhand. I'm like, what are all these like crazy particles? All right, U C, U bar, S bar, and then C bar S. Goes to pi naught, J psi. Thank you, sir. This one, you can draw most of them across. If you try to do it by like annihilating everything, I think I was nice and still gave I think I still gave credit to people who use too many gluons. Really nice people. I'm just that nice guy. But you really don't need very many gluons because most of these connect across. That U goes there, the C goes there, the U bar goes there, the C bar goes there, right? So what you have left is a UU bar pair and an SS bar pair. Both of those can be dealt with by annihilating to a gluon that then gets absorbed by something. And any quark line can absorb a gluon, right? So it doesn't really particularly matter where it goes. So any of them can absorb a gluon.
Why did you erase it?
I believe I still give you credit, even though some people did some more creative things with gluons. I saw some 4-gluon vertices which I thought were odd. Then I saw several of them. So were you guys copying off each other or what?
Yes.
I mean, I did mention in class, but I also said you never use it. All right, whatever.
I used to a lot of the
What?
I didn't really use it.
Good.
Yeah.
He did it that way. I mean, yeah, you do exactly the same. It's actually not. It's got more vertices. But I let you go on. So maybe you like the same number of blue ones. This is 1, 2, 3, 4. Like if you did 5, but then just
What's the symbol for
that's
iron?
true, but it's still not the highest order. I was very nice to you. You're welcome. So,
Thank you.
C bar not, all these crazy particles. No one ever uses. Thank you, sir. Okay, so this one, you cannot draw anything across, making it substantially more difficult. Actually, overall as a class, I thought we did pretty well on this, but a lot of people are trouble because this is actually quite a difficult diagram. Well, one of the most difficult that you can come up with. To do it, you can see that there's got to be W's going on, right? And in fact, a lot of people realize correctly that you just need a lot of W's. those of you who tried to use either gluons or Z's, that doesn't work because gluons or Z's or photons or anything else cannot change flavor. Only W's change flavor, right? And so if you try to use anything but W's, it's not going to help. Only the W's can change flavor. But what do you do? Well, probably the simplest way is to take the UV bar annihilates to a W plus and have that form one of those guys. That's an S bar. The US bar annihilates to another W plus and goes over here. And then what a lot of people wanted to do was then say, oh, now the UC bar annihilates to, but it doesn't, right? Because U is a charge, because U and C have the same charge, right? So this is plus 2/3, this is minus, well, sorry, this is charge plus 2/3, this is an antiparticle, it's a charge of minus 2/3. And so the total charge would be 0. They cannot annihilate to a W, right? U and C cannot go together to form a W. So instead, what you have to do is, and then you try to make the W, and then you have the same problem on the other side. There is no neutral W. There is no neutral particle that can change flavors. You have to use the W's to do it. So the way you do it is you have this guy emit a W plus, which changes the flavor from U to D, and then the C bar can absorb the W plus through a CKN vertex, which changes the flavor to B bar. There's another CKN vertex here. No matter what, you need 2 CKN vertices to make this flavor. All right. And then for number 6, can I see someone's again? Just need to do that. Thank you. I was pretty generous on this one too, I thought. So proton, J psi goes to I plus, D minus, lambda plus C. Okay. Now drawing the diagram should be pretty straightforward. Most of these draw right away. And was this the class? Was that you? That was you, right? Okay, yeah, that's right. The bizarre triboson thing going on. Okay, yeah, I didn't know what to do. I didn't know what to do with that either. You just left that out, it would have been fine.
You realize that my Chinese is very
it's just traditional.
Yeah.
Okay. He writes those to me in Chinese, so I thought it was fair. Okay, so and then to do this, you would just radiate a gluon from somewhere, say here, would do. And you get that. Now, the tricky part is getting the colors on here. Getting the colors on here is not that easy. There's a few rules you have to follow, and a lot of people forgot at least one of them. If you forgot too many, then you didn't get any credit. Depending on what I saw, I gave some amount of credit for different things. But you have to remember, all these particles, what has to be true about these particles? They have to be colorless. So the mesons will have to be something like red anti-red or green anti-green. They can't be red anti-green, that would be colorless. The hadrons have to be like RGB, some combination of, in some order, they have to be RGB, right? In addition, color has to be conserved in every vertex. There's only 2 vertices to work on. And then, what's the color of a gluon? No, they're not colorless. Gluons have a color and an anti-color, and they're not the same. We went over this in class. Gluons have a color and anti-color, and they can't be the same. Gluons are not colorless. They are always colored. So, so to do this, you have to be careful. So let's start with this. If I label these arbitrarily R, G, and B here, right? Now, if it's the same line, then it has to stay the same line. So that R here has to become R here. It's the same color, nothing's changed. This B here has to go to a B down here, right? But, hang on, do I have to change already? No, this should be okay, yes. Okay, now, here's the thing. I need to make this gluon colored as well, right? Since I have a G going in like this, then the gluon color has to have a G in it. I'm going to make a GR bar. To conserve color, if this is G to begin with, then afterwards the total color has to be G. So this is GR bar, and the color of this one has to be R, because if you put those in the R bar cancel, you'll just have the color of G. See, so the total color stays the same. We've created an R and an anti-R here, but they're split across these two different particles. Yes, Maddie?
Is there a reason why you like did the gluon first?
Why did the gluon, sorry?
Like why you chose the color for the gluon and then the carbon color?
You have to make sure it all works. So that's I'm just trying to be careful on that. I think this will not work. Everyone's version is going to look slightly different. Depending how you do it. So then this one now is an R particle, right? It changed colors when it emitted the gluon. And since the gluon's colored and color is conserved, that's what has to happen. Whenever it emits the gluon, it has to change color. So this changes color, now this is color R. Here, you have R bar and G. They split, right? So if this is R bar and G, this guy gets the R bar, and this guy gets the G. That's why I chose R bar, because now this makes an R bar, and that's a colorless combination. If this is the G, what's the color of this fork have to be? G bar, right? If this is a G bar, tracing back to here, this has to be a G bar. If this is a G bar, this has to be a G. And that makes it a G. Oh, good. And this is the colorless combination. So this is not the only way, but they're all going to look about like this. All of these are colorless combinations of colors. And the color is conserved at this vertex, and the gluon has a color and anticolor that are not the same. Tricky question, huh? Okay, good. So, any questions on the quiz? Yeah. Let me see. For which one? Oh, you have an extra gluon. Doesn't need to do that. Remember I told you about those extra gluons? Just glue like it with one X out. You don't need it, right? You can do it all. Number 5, you can do all the W's. You had an extra gluon that didn't need to be there, so I think I got some points on that. A few people did that. Right? You can just, if you just angle that line differently, then there's no need for a gluon at all. The gluon is superfluous, so you didn't actually need it. Okay, any other questions on the test? Okay, so let me take these back.
Yes, nice.
No.
Guess what I found?
You did not.
The sign is positive for photons and negative for electrons. Photons are hadronic, electrons are, right?
You mean protons, right?
Yeah, photons are hadronic. Guess what these are? The reduced equations. This is one of these is electronic, one of these is electronic.
The redemption quiz, like I said, man.
And they both end at 15.
That's everyone's, right? Do I have everyone's?
Sort of. They haven't
The
actually
redemption
put it
quiz,
here,
like I said, is not
everything here.
until December. And the remainder of this unit will not build heavily off of this stuff, which is really usually not something you cover till like junior year of college or something. But it's fun, right? Yeah, definitely fun. So this is not like, I'm going to make reference to quantum diagrams plenty of times, especially when we're doing the detector project, but this is not going to directly be something that the rest of the quantum mechanics unit builds on. Okay, because it's kind of a separate thing. So you can consider that good or bad, but it is what it is. Okay, how's that homework?
Okay, talking about the Dirac notation.
Let's talk about it and see where we are. Say happy to show the class something. Can you show the class something?
Yes.
Okay. Go ahead.
Yes.
Oh, yeah, yeah, okay. Wait, yeah, yeah. Thank you. And they have a presentation.
Presentation is a strong word.
What?
Wait.
Oh.
Okay, we are I see. Very nice. Well done.
That was okay.
What we call those your arrows? Nice. Are you going for the geekiest costume prize or something like that?
Yeah.
Because they have one.
I mean, either one.
Okay. So I'm making a problem here.
Wait a second. I could totally pass this direct.
So I can't seem to find my answer key.
Oh, Derek.
I'm not sure where it is.
Bell Rock.
Oh, this is not what I'm looking for.
That is.
No, it's not.
Go back up.
No, it's not.
That.
No, it's not.
Why not?
Because.
There it is
So
again.
I can't quite do these in my head, but maybe you guys can just tell me what you have and go from there. What do you have for number one?
Negative 26 plus 14i.
Okay, 26 to 14i. Is that something you guys? Okay, that's great. How about two?
4 minus 14i.
Okay. If you disagree, let me know. They might be wrong. Okay. Number three? 108.
What?
Now for purple. Yeah, okay. Number four? 136. Okay. Okay. Number five. Okay, these I can do a lot faster. Number five would be negative cat 1 plus 2 cat 2.
What's the cat?
Minus the quantity 5 plus 8i cat 3 plus 8i cat 4.
I don't know. I don't even know anything.
Oh, yeah, sorry, I got that wrong. Which one's good? Negative 1 plus 4 cat 2. Sorry. Plus the quantity negative 5 plus 8i cat 3 minus 8i cat 4.
Yeah, no.
Is the stuff on the board, or is that the answers to the quiz?
Yes.
Are they really?
However you do that term might have a few different versions, but you're all fine.
I don't want this.
Number
Here you
6 is
Put
3.
it on the back.
Number 7 is negative 1. Number 8 is negative 1. Number 9 is a pain. Hang on. Is 11. Is that right? Oh, sorry, looking at the wrong thing. Yeah. Let's see. 3 minus I. Yeah, that's right. 3 minus I. Number 10. Is it 64 squared? No. What do you have?
We have 1,609. It's like $1,000.
Right, but it's got absolute value squared, right?
I thought that was magnitude squared.
Magnitude squared, that's a positive number either way, right?
Yeah.
Okay, hey, let's review things. I'm sorry I wasn't here, like, conference couldn't get to that. We'd already agreed to do it back in like April, so I had to do it. But let's talk a little bit about it. It's just a review. Maybe this problem is possibly. For a complex number at the volume phi, magnitude of phi squared. Wait, no, you did this right the other time, though, right? Is a plus bi times a minus bi. Remember that from math class?
No.
The square of a complex number, or you take the magnitude square of a complex number, it's complex number times its complex conjugate. So the complex conjugate is the same thing, but with all the imaginary terms reversed, all the i's and negative i's. When you do this, by the way, in general, you get difference of squared, right? A squared minus bi squared, which is say plus b squared. And the reason you do this is, what can you tell me about the quantity a squared plus b squared if a and b are real?
And
This is something that is positive and also
real,
right? So the magnitude squared of a complex number is always a positive real number, thus making it useful as a magnitude, something that's positive and real. So, so this is how you do. Yeah, that's right. You did this part fine on the earlier one. Okay, so if you want to take, then you should take someone. If you take this one, right? Don't you get? I don't have the things with me. Didn't you get something like negative 24i minus 40i? Is that what you get? Is that what you get? Maybe I did the wrong thing. Hang on. I get confused.
Don't we all?
Oh, yeah.
ModPhys. When are we not confused?
Okay. So that clears things up. Okay, so then the answer is, yeah, 1609. Good. So it's not that, right? So the answer is 1609. Okay.
Alright.
What should I go over? What? Do this one? Okay. So. Someone have those things down.
Let's tell stories about Richard Feynman.
We're not gonna do that.
Why not? You don't know.
Because you have better things to do.
No. It's Spook Day.
Okay, what are these funny arrow things called again? No, these are called pets. These are called pets.
Why are they called tech?
Why are they called that? Because, and then the other version is called a bra. It's pronounced bra. You might hope desperately that it would be pronounced bra, but it's not. It's pronounced bra. So let's stop there. Rocket notation? Yes, they call it rocket notation.
That sounds like something.
So, did you guys get enough time to get the like dumb bra jokes out yet? No, we'll get them out. Don't worry. Broccoli. So imagine some weird combination of this with E. coli. It makes broccoli. Right, anyway. So,
that's
change your head into a bra. You just switch the direction. But when you do that, you have to make sure to take the complex conjugate of all coefficients. Fortunately, in this case, this all has real coefficients, so nothing's going to change. So you change the cat into a bra, everything looks the same. Except all the cats turn into bras. But you have to remember, in general, you take the complex conjugate of each of these coefficients. It's just these are all real numbers, so it doesn't matter right now. Yes?
Is there like a new line for that same number?
You can probably come up with one. I don't actually know one. Cats are what we normally use. Cats are what we spend most of our time using. Those ones pointing to the right. Well, the mnemonic device is bra ket, right? And so together they form a bracket.
Wow.
It's bracket.
Couldn't they have just added
Notice, Paul Dirac would mention this was a theorist, and what do we know about theorist naming?
Oh, the
Words. That's right. They're no good at it. So this is another example, perhaps one of the most egregious examples, because Paul Dirac obviously never had to teach high school and say the word bra repeatedly over and over. And so.
You're doing worse with this word than we are.
That's fair. So this is the bracket. This is the question asked for, right? Let's start by just working out what is this. Let's square it in a moment. But let's just work out this bracket, right? To work out a bracket, it's very simple. It's just a bra times a ket, right? So I have the bra here. I can just substitute that in. And I have a ket here. So it's the side 1 bra, and here's the side 2 ket. Oops, wow, -2, there we go. That's 8, 9, 3. And you multiply them together. Now, these of course are, the bras and kets you can treat just like variables, right? They work just like variables, they behave always just like variables. So you can combine them just like variables. So you look, you have a trinomial times another trinomial, you're going to end up with how many terms? Come on guys, this is not. Someone? 9, thank you. Okay. That was not supposed to be the hard part, guys. Okay, so, they'll simplify, but in general they'll be 9 terms, right, to begin with. So just this once, I'll write out all 9 terms for you, okay? And then we will simplify in the future. So, you have -1 times -2, because so it's bra 1, ket 2, right? And the negatives cancel out, so you end up with that, right? So that was that times that. And this times this. What do you call the FOIL thing when it's a trinomial?
It's so foil.
extreme foil.
Double distribution. That one's not as catchy as FOIL.
It's just
Yeah,
distribution.
didn't everyone here learn FOIL?
Yeah.
That's the name for it.
That's not the name for it.
I know, but did everyone learn it as a name for it?
Yeah.
Right? Okay, so just sort of curious.
Wait, Phil only would work with binomial.
The next
Yeah.
one, now this one times this one is,
like,
when you do this, the constants can always go to the front. So you have
like-
-1 times -8i gives you positive 8i, and then bra 1 ket 3, like that. You see where that came from?
What?
It's not hard. I just want to make sure we got it right.
Uh-huh.
You take the negative bra 1 times -8i ket 3. You put the constant term in the front, and you have 2 negative signs, they cancel, and then you have bra 1 ket. Does that seem right? So this next one, you have a negative bra 1 times a plus 8i ket 4. So you have negative 8i bra 1 ket 4. Like so. I can't tell what the silence means. Are we, does this make sense?
I'm internally panicking.
What?
I'm internally panicking, so.
You're totally panicking?
Yeah. That's why
Well,
I'm-
start doing it externally, then I know. That's not what I meant. You ask a question. Okay, no, this is not hard. This is not hard. If you're panicking, it's just weird notation. Okay? All you're doing is distribution. Right? These things are like variables, right? Just like different variables. The guys in front of them are just regular coefficients. So all you're doing is multiplying this times this, right? You have regular coefficients, there's a -1, there's an 8i, so that gives you negative 8i. And then the rest you just combine. Here's a 1 bra, here is a 4 ket. You just put them next to each other like that. Yes. Of course you could do that, yes, but I want to write this out, and I want to get this out in detail so we understand what's happening. Yes.
So how do you simplify it?
Oh, we will, but let me finish writing out the terms.
Okay.
I just want to make sure we understand where the terms come from. Like, are we okay on that? Like, you see where the terms are coming from? You just multiply the coefficients, put the bra next to the ket. right? So, for example, the next
This
one,
multiplied by this.
so we're not done yet, right? Is this times this. So, the coefficients are 3 times negative 1, so you'll get negative 3, and
That's
then you
two.
have a broad, 2 broad and 2 ket, so it's bracket 2 to 2. Then we have this with this, so the coefficients are 3 times negative 8i, which gives you negative 24i, broad 2, ket 3. And then this one gives you 3 times 8i, so plus 24i, broad 2, ket 4. And we're still going. Right, and this times this is negative 5 times negative 1, so plus 5, broad 3, ket 2. Negative, then this times this, you don't have to pay attention to this anymore. Negative 5 times negative 8i is plus 40i, broad 3, ket 3. And then negative 5 times this 8i gives you negative 40i, broad 3, ket 4. 9 terms as promised, right? And while it's kind of a pain to write them all out, it was doable, right? You just take each pair, you multiply the coefficients, and then you put the broad next to the ket.
Is it possible to put this into summation?
You okay with that part? Good. Now, in the future, you probably will do these faster, but this is the complete way of doing it. Now, here's the rule, in case you forgot. The broad of A with B, where A and B are two different things, and the bracket, excuse me, of A with B, where A and B are two different things, is 0. The bracket of A with A is 1.
Is that it?
Okay, so
What about
you-
B with B?
Also 1. So in other words, if these two are the same, then you get 1. If these two are different, you get 0. So it's remarkably easy to work with, right? In fact, some of you are like, oh, then why are you bother writing out all of those things? Well, I just wanted to show you. You're welcome to go faster if you understand it. But bracket of 1 and 2, therefore, equals what? 0, because they're different. So that one's 0. 1 and 3? 0 also. 1 and 4? 0 also. 2 and 2. That one gives you 1. So this one goes to 1. This one stays, right? 2 and 3? 0. 2 and 4? 0. 3 with 2? 0. 3 with 3? Aha, these are the same, so that goes to 1. And then 3 with 4? 0. Okay? So we wrote out a lot of terms, but almost all of them are 0. That's what I said, it simplifies. So, what do you have that's left? Well, here we have negative 3 times 1. So, negative 3. And then down here, we have 40i times 1. So, plus 40i. Good question?
What happens if you have a number? Never mind.
That might be a good question. Pronunciation of the number.
There is a question there, but I'm not entirely sure how I want to phrase that question with it making sense and not sounding like a completely stupid question.
I relate.
There's no such thing as a stupid question.
That
Totally
is
fair,
false.
right? Of course it's a fair question. But I don't think that's a stupid question if you need to clarify what's going on, right? Right. So let me see if I can answer one question. Okay. This is actually not completely true because you're like, wait a minute, side 1, side 2, wouldn't that be 0 because they're different? So the answer is okay, wait, you have to be a little bit careful. This rule only works when they're kind of reduced to their basic form. Soon we'll have a nice way of saying what their basic form means.
That's answering my question.
Okay. So soon we'll have a nice way of saying what exactly I mean by their basic forms. It means their eigenstates of the same operator. But until we get there, then we can just say that they all have to be in the same basically reduced form. Okay. Once we have that, then the last question is what is this square, right?
Oh.
That was actually what the question was asking for. What is that one square? So we found what the bracket was. Working inside out as you're supposed to. Hey, wait, are you guys children of the Pluto-less generation?
What?
You are, right?
Well, not after 2000.
What mnemonic did they give you to memorize the planets then?
Oh.
It's supposed to be my very eccentric mother just sent us 9 pizzas.
That's what I figured.
Yeah.
I just remember
My
the
very
planets.
eccentric mother
My very
just.
eccentric mother just sent us nothing.
Concept of like the number 9.
Just sent us 9. I see. All right, so we're going to take this as
Just
square.
sent us
Right,
notes.
that means it's going to be negative 3 plus
That sounds
40i
illegal.
times negative 3
Here,
minus
have my nib.
40i. Because you multiply by its complex conjugate, right? So the real part stays the same, the imaginary part changes sign. And then, when you work this out, you use difference of squares, negative 3 times negative 3 is 9. 40i times negative 40i gives you minus, but then I squared equals plus, 40 squared was 1600, so that gives you 1609. Yeah.
Is there, like, what happens when it's more complicated? Like, we have like over
It never really gets much more complicated than this. This is actually the extent of the math. Well, you might have fractions to deal with. Right, but aside from that, the main thing is understanding how these steps work. Now, look, you could see like, wait a minute, why did I write on all 9 terms if only 2 of them are non-zero? And that's cool. You could have skipped to this step once you realize that, right? But you start with this so you understand it, and then you can, once you feel like you understand it, then it's fine to skip to skip straight to it's fine. Okay. Should it have transpired that you didn't actually do the homework for whatever reason, you should do it. Okay? It is foundational and very, very important to make sure you know how to do this stuff. Okay. Great. What's it supposed to work today? Yeah, I know. I was feeling it was something short. I kind of cold. Let me see. And is that still confidence within you? That's confidence with you doing. Totally on top of it. Ah, yes. Let me show you something. This is really convenient. Dr. Ponce just happened to have these set up for Sunset Light.
Oh boy.
I want to show you something important about light.
Oh no.
What we have over here is a laser. This one's got the green one.
Oh, there's still 4 1.
All right. So,
Oh boy.
see the laser? Oh wow, this lasts very long. Let's try it. Let's look at the other light. The contrast will help you see it. Okay. Yes, it's dark. That's not only about the lights. So here's the real laser seems to show up. The battery's dying or something. So here's the laser. See it?
Yes.
Okay, good. Any questions? Okay, so now up here you can't see it, but I have on this little piece of paper 2 slits that are very, very close together. Okay, 2 slits that are very, very close together. And now I'm going to shine the laser through the slits. Whoa. I had it for a moment. Okay, now what do you see? I see like a bunch of dots, right? Let me see if I can get a nicer one. A little bit hot. Okay. Pretty good one. I'm trying to do it with these will last very long.
Around the laser campfire.
So, there's the green one. Okay, so here's the thing. When you shine one of these things through slits, what do you not see? How many slits did I say there were?
2.
2. What do you not see on the wall?
2.
You don't see 2 lines. How many do you see? A bunch. Okay, there's more than 4. Okay? There's a bunch of slits in the far wall. Okay, go ahead and turn this on. Thank you. Okay. that demonstration is something that was done. That was done originally by Thomas Young in the early 1800s. He didn't have a laser. It's a lot harder without a laser. But it illustrates an important principle called interference. Okay, I can cover the stats. It's not hard. Here's how interference works. This is the side view. There's a light here. There's two slits here, and then there's a wall over here. Okay? Now here's what happens. If you were just shooting machine gun, you were throwing rocks at a wall with two holes in it, right? And then you looked on the other side to see what pattern the rocks made on the other side. What would you see? You see two piles of rocks, right? The other ones would bounce off the wall, right? The ones that went through would either go here or here, right? When Thomas Young tries this with light, he does not see just two dots, just like we did, right? Instead, he sees a bunch of dots. Where do those come from? Well, we can see this in other things, like for example, the wall. This is something that is a property of wave behavior. Here's what happens if you have a wave going through two slits. One wave goes this way, and one wave goes this way, right? Now, when they go through the splits, then you guys all know what waves are, right? Come to the next slide, right?
Yeah.
Okay, so when they go through the slits, consider the waves that end up at this point. Right? Well, when two waves meet, what do?
Cry.
You know what they do? They add. It's as simple as that. So what happens here is that there's a wave here and then there's another wave here, and they add together to make what? A bigger wave. Good. Right? You add two sine waves together, you get a bigger sine wave. The peak gets higher and the low peak gets lower, right? So you get a bigger sine wave. Good. This is referred to as constructive interference. The waves interfere with each other, they interact with each other. But when they do so in such a way to make the waves bigger. So we call it constructive interference. Okay, now, that's what happens right in the center. But now consider a point somewhere off center, like over here. Now consider these two waves are now going different distances, right? Right, you see this distance is not the same as that distance. So there's now a difference in distance, and so now you have this one wave going along like this, right? The other wave is the same wave, but since it's gone a different distance, it's starting at a different place, right? So it looks something like, in particular, it can look something like this. You see that? Same wave, but just offset. Okay, they refer to it as a phase shift, or they call it out of phase. Okay, do you see how that is? It's the exact same wave. I just started this one a little bit later. But when I start this one a little bit later, what happens when you add these together? What do you get when you add this together?
They cancel each other
These
out.
cancel out to zero, right? The peaks and the troughs line up in exactly the wrong way. These cancel out to zero. So this equals a flat line. And we refer to this as destructive interference.
Sounds like constructive criticism.
Yes. Not destructive, not deconstructive. That's what people always say. Deconstruction is a literary theory. This is destructive. Okay? We're not going all postmodern on this. Actually, quantum mechanics is really very postmodern, though. Okay? So, you get destructive interference at some point. And then, if you go further away, like down to here, sorry, what's going to happen here is still the same two waves, but the difference between them is changing, right? When you go to a different spot on the wall. And so here, you can make it so that this one starts at a different point. But when it starts here, what happens when these two waves meet?
It's constructive.
Now they line up again, right? Basically, they start to shift, they start to get out of phase, right? They're not lined up. Here, they're perfectly not lined up, right? And it cancels out. But if you keep on going, the wave is periodic, so eventually it lines up again. And what happens when it lines up again? Constructive interference again. And then, as you go further down, it's going to get further out, and what's going to happen? Destructive interference, and then constructive interference, and then destructive, right? So you're basically alternating constructive, destructive, constructive, destructive. Okay, now, we're talking about light hitting the wall. When it's constructive interference, what are we going to see? A brighter spot. When it's destructive interference, what are we going to see? See nothing. We're going to see darkness. So, what you end up with then is a pattern of bright light, nothing, light, nothing, light, nothing. And the pattern goes in both directions. And you end up with a pattern of dots like this. Yeah.
Is there a relationship between the distance of the dots and, because I realize the distance.
Yeah, and everything else? Yes,
yeah.
there is. There absolutely is. And I was just about to tell you that. So, well done. It's a very easy equation. The actual details of this are mathematically complicated, but because this distance tends to be very large and this distance tends to be very small, you can get a nice approximation of this that works well. And that is this. Let's say that this distance from the slits to the screen is L. Okay? The distance between the two slits is D. Okay? And, wow, I have nowhere left to draw. The distance between, X tangent, I'll just write it. And then delta Y we'll call the distance between two consecutive bright spots. Okay? That's from a bright spot to another bright spot. That's to say from constructive to another constructive spot. That's delta Y. Okay? And finally, lambda. Do you remember what lambda means for waves? Wavelength. That's right. Lambda is the wavelength. Okay? Then the equation is delta Y equals lambda L over D. It's not a bad equation, right?
No, not at all.
I'm gonna hate it later.
It's not a hard equation. You have to make sure everything's the same units. Put everything in meters. It's probably the safest way. Because typically lambda is given in nanometers. This is given in meters. This is given in millimeters. This is given in centimeters. Like it's often like this around. So just make sure to get them all in the same units, right? But once you're there, that's a very simple equation, right? Okay, that's all you need for your homework.
Wait, when you say homework,
The homework on Moodle.
Yeah, that's why. That's all you need for your homework. We will talk more about the importance of adult experiment later.
yeah.
Thank you.